once again. I won't in detail like specific molecules, but roughly the bond pair, lone pair, I can just like go over it. Okay. So VSEPR. So if let's say you have 2 bond pairs and 0 lone pairs. So 2 bond pairs matlab you have a central atom and you have 2 pairs of bonded electrons. It's bonded to 2 different atoms. So the form AX2. Then it is going to take the most symmetrical shape ever. So you have your central atom here and the 2 X atoms are going to be far away from each other. So this is the shape it's going to take. And what will be the name of this shape?
Linear.
Linear. Linear because it looks like a straight line. Okay. Then let's say you still have 2 bond pairs. This time we have 3 bond pairs and no lone pairs. So 3 bond pairs matlab central atom is bonded to 3 different atoms. Now, how will the 3 bonded pairs be arranged to have like the maximum space between them? Where should I place 3 of them so that they have maximum shape? Is it going to be T shape?
In the shape of a triangle.
In the shape of a triangle, absolutely. Okay. Now, because it is a triangle, it's going to be a perfectly symmetrical triangle. Angle between them is 120. So 120, 120, 120. So this shape, so 3 of them, all of them are in the same plane. So it's trigonal. Tri, 3 sides, gonal. So it's like polygon ka gon. So like 3-sided shape. It's trigonal. And because all of them are in the same plane, trigonal planar. 3 pairs of electrons again, but this time it is 2 bond pairs and 1 lone pair. 2 bond pair hai, so it's of the form AX2 again. Now, how will the 3 electron pairs be arranged so that all of them are far away from each other?
And shape.
Same. Yeah.
Same, except one of them is a lone pair, right? So the X atoms will only be over here and over here. And the 3rd electron pair is a lone pair that's just on this thing. Okay. So the electron geometry is trigonal planar because they're there in like it's a 3-sided figure, triangular shape. But the molecular geometry is going to be, what shape is this?
Trigonal planar.
यहाँ पे तीसरा side किधर है? We're talking about molecular geometry.
It will be a bent.
Molecule. Straight line nahi hai. It's this way now. It's a bent molecule. It's bent. It's bent like this. Okay. So molecular geometry matlab shape of the molecule. You just focus on the atoms here. Electronic geometry matlab you focus on how the electrons are arranged. So that's the basic difference. Yeah.
So in molecular geometry, you just talk about the angle and stuff that the bond pairs are making. And in
Yes.
electron geometry, it includes the lone pairs also.
Correct. Yes. 4 bond pairs and 0 lone pairs. So it's of the form AX4. Central atom idhar hai. So all 4 of them, how will they be arranged?
Tetrahedron.
Tetrahedron. It won't be a square because we're looking at 3-dimensional shape, 3D here. Like in space, how will 4 of them be aligned? You need to look at that. So it's going to be tetrahedral geometry. So tetrahedron basically looks like this. If these two are like this in the same plane, then एक आगे की तरफ होगा and then एक पीछे की तरफ होगा. Okay, so tetrahedron is basically like a pyramid with triangle at the base. You can think of it as a triangular pyramid. So that's a tetrahedron. So these three of them form a triangle, and the topmost point is, it's like a pyramid. Center says straight line draw karo, and then yeah, so that's the tetrahedron shape. Okay, abhi 4 pairs of electrons hai, but this time only 3 of them are bond pairs and 1 is a lone pair. So formula is AX3 kyunki 3 hi hai bond pairs. What will be the shape of the molecule? Electron geometry is going to be tetrahedron only, but inme se one of them is a lone pair. So ek bond nahi hoga. So then what is the shape of the molecule?
Trigonal pyramid.
Trigonal pyramidal, yes. So this time it's a proper pyramid. So ye teen idhar hi rahenge, but the top one, the 3 of them form like the pyramid, but this bond pair is not there. So instead it's the lone pair of the central atom itself. So it looks like a pyramid except the base is a triangle. So again, it's trigonal. So you have a 3-sided figure, but it's not, they're not in the same plane. It is in the shape of a pyramid. So pyramidal. Okay. So that's how you get for 4 bond pairs, 5 bond pairs, like sab kuch, like this the whole set of things. But go through each one. There is a definite logic to it. These names are like technical names. You have to remember it. You can't make up your own name. So you need to by heart it. But by hearting is not going to be difficult. It follows a certain logic. So if you are able to imagine the shape, you can come close to the name. It'll be easy to remember the names once you figure out the shapes. Okay? Now,
Ma'am, I don't know, have you gone over this again or not? But could you just again explain what was a pi bond and a sigma bond?
yeah, that is the next part I'm coming. So that's all part of VBT. Okay. So VSEPR is capable of only telling you the shape of the molecules. You can visualize how the bonds are arranged, how the electrons are arranged, how the individual atoms are arranged. But in the case, but it's not telling you anything else about, just a moment. So it's not telling you anything else about which particular orbitals are, or which particular electrons are basically being shared between the 2 atoms. Now again, electrons repel each other, right? So how are the more like atomic orbitals being aligned in such a case? So it's not going into that detail. So if you want all of those details, VBT is the one providing it. Okay, so the base of VBT, like mathematically, we had gone through it that, if you have 2 atoms, like if you take the simplest case of 2 hydrogen atoms coming close to each other, this is coming this side, this is coming this side, then as the distance between them approaches, we have seen what all forces come into play between these individual atoms. We've seen how those forces affect the stability of the system itself. So we drew this whole energy diagram also. Like when they're far away, it's pretty stable. As they come close, you have like the attractive forces of the nucleus acting on each other. So the energy slowly goes down. But if they start getting too close to each other, as the distance increases, the energy also increases by a lot. So the bond takes place where the energy is minimum. So this is the distance at which the bond is possible. So this is all like the mathematical energy-based calculation, like energy explanations with respect to this. Okay. Just going into somewhat more detail. According to valence bond theory, what is happening is there is overlap of the atomic orbitals. So this is what we call the covalent bond or chemical bond. Covalent bond is nothing but you have, let's say, s orbital of one electron, s orbital of the other electrons, basically electron clouds, right? So when those clouds overlap with each other, that's when we say there is a bond being formed between the atoms. So the keyword being overlap. So we're just going to look at the simplest cases, which is overlap of s and p orbitals. So there are two types of overlap. You have your sigma overlap and you have your pi overlap. Okay. So sigma overlap is when it happens along the same axis. Pi overlap happens above and below the axis.
Ma'am, I had a doubt. So the graph that you made, is that the energy graph of an electron?
Yeah, so overall energy of the system, and x-axis is the distance between the atoms. So where the energy is minimum, that's where this is the distance at which the bond is formed. Yeah. Anyway, so coming to the overlap, sigma overlap happens along the same axis. Matlab, you have, let's say, s orbital of this one atom, and you're taking another atom in the same line. So when both the s orbitals overlap, so the nuclei, the overlap, all of them are in the same line. So that's what we say, it's happening along the same axis. Same is the case with when p orbitals overlap also. Like s orbital is spherical, it's uniform all in the same way. Nucleus of the other one is also in the same line, and the overlap is also happening in the same line. So nucleus 1, nucleus 2, and overlap. If all of them are along the same line, so that's a sigma overlap. So this is SS sigma. This is SP sigma. Similarly, you can have a PP sigma also. So first atom ka p orbital, nucleus is line pe hai. Second atom ka orbital, nucleus same line pe hai, and overlap is also in the same line. So this is a PP sigma overlap. Now coming to pi overlap, like let's say this is the line where the nuclei are there. The overlap is happening above and below this thing. Let's say this is the nucleus. So upar or niche ho raha hai, it's not in the same line of the nucleus. So this is a PP pi overlap. Okay. So now, are you clear about the difference between sigma and pi overlaps?
Ma'am,
Yeah,
there can never be an SS pi overlap, right?
never, no. So SS, because spherical hai na, so like overlap to along the same line to ho hi jayega. So there can never be an SS pi overlap.
And ma'am, how do we like identify if the electron or the orbital is a pi or a sigma bond?
Yeah, that's a good question, Nishit. So first, you're clear about identifying which is a sigma overlap, which is a pi overlap based on how the overlap is.
Yes.
Yeah. Okay. Now, there are some differences between sigma and pi overlap. Like, I'll give you this thing. Okay. First point of difference is, which type of overlap do you think will be stronger, sigma or pi?
Sigma.
Does everyone agree?
Yes, ma'am.
Yes.
Yeah, it's sigma overlap because, this is pretty strong, right? For the pi thing, like upper, niche, you need to like bend over and lots of things. So yes, sigma overlap is definitely stronger because you can even make it stronger by overlapping as much as possible, which is not possible with pi overlap. Like there's a little bit of restriction. And the second thing is, in which case is the rotation of bond possible, in sigma or pi? In which case am I able to rotate the bond? Like if I have atom one,
Sigma.
sigma because it's along the axis, like even if I turn this around, it's not going to affect the overlap. Pi ke case mein upar niche ho raha hai. If I want to rotate one of the atoms, ye bond break ho raha hai, right? So sigma overlap is stronger and rotation is possible, which is why sigma overlap is always preferred. Okay, so whenever two atoms get ready for chemical bonding, your first preference is always for a sigma overlap. So the first bond, whenever it happens, single bond, double bond, triple bond, whatever bond is there, your first bond is always a sigma overlap. And then if there is a second bond, like in the case of double bonds or triple bonds, that is going to be pi overlap. Okay. So hamesha your first bond, whether it's in single bond, double bond or triple bond, pehla bond hamesha sigma hi hoga. Then if a second bond or a third bond is required, like a double bond के केस में दो bonds है, triple bond के केस में तीन है ना. So the first one is always sigma and the remaining others are always pi overlap. Okay. So I'll discuss like 3 examples, like one for each case, for sigma, for single bond, double bond and triple bond. It'll get clearer. The first example is, let's say chlorine molecule form hona hai. What is the electronic configuration of chlorine? Guys, are you there? Are you with me? Following?
Which type of electronic configuration, the SP or the normal one?
SP1, like proper, expanded. Because we're talking about sigma pi atomic orbitals, no? So give me the whole thing.
And I guess it's 1s, 1s2, 2s2, 2p6, and then 3s2, and then 3p5.
3p5. Yeah. All of these are inner electrons. They will not bother with the bonding. So let's look at the incomplete shell, 3p5n. So how are the 5 electrons in the 3p orbital arranged? Yeah, this part, this one will be half filled or fully filled?
The first one will be fully filled.
Fully filled.
Okay. And the second one?
Second also fully
Fully
filled.
filled.
Yes.
again.
And this
Half filled now.
not
Half.
filled, right?
Half of it.
So इनमें से which one is ready for bonding?
The last one.
Yeah, the single unpaired electron जो है, this is ready to take part in bonding. So we have 2 chlorine atoms making up this thing, right? So chlorine में what type of bond is there between both the chlorine atoms?
PP overlap.
Single bond. किस तरह
Single bond.
chlorine single bond is present. Only 1 electron is shared by each. So there's 1 pair of electrons. So what happens is, पहला chlorine का जो half filled p orbital है, so that particular p orbital will align itself this way. Then दूसरा chlorine का again half filled p orbital will align itself along the same axis, and there is an orbital overlap between them. Okay, so this one nucleus is over here, this one's nucleus is over here. So these other two, like if we call them px and py and call them pz, so it's the pz orbital of both the chlorine atoms aligning themselves along the same axis to form a sigma overlap. Always your first bond is sigma overlap. Remaining px, py are still there, but because they have pura electron, they're not bothered. Like they're just there perpendicular to the other thing. So only the half-filled ones, the atoms will align themselves such that their half-filled orbitals are facing each other, and then they do that overlap. Okay. So we call this.
I might have a doubt.
Yeah.
How do you know if a compound has say a sigma overlap or the pi overlap? How do you tell the difference in the formula?
Simple. If it's a single bond, that's always a sigma overlap. If there is a double bond, the first one is a sigma overlap and the second one is a pi overlap. And if there is a triple bond, the first one is a sigma overlap and the other two are pi overlaps. Okay, so that's why I'm discussing each example one by one. So single bond में हमेशा पहला वाला sigma overlap ही होगा. So the first preference is always for sigma. Like if it was physically possible for every overlap to be sigma overlap, they would go for it. But unfortunately, rules of the real life universe is that along the axis, agar ek sigma overlap hai, so that's all, they're done. So the other bonds will have to be pi overlaps. Okay, so that's what we'll be looking at. So this is the first example. Now let's look
Write this
at
down, right?
what?
We write this down, right?
You can notice some, yeah. Note down. Yeah.
So like if the px and py also had to share, then there would be like a double or a triple bond. So in that case, it would be 2 pi, like 2 sigma and 1 sigma and 2 pi, or 1 sigma and 1 pi.
Correct, absolutely. And that's what we'll be discussing right now. So pehla ho gaya chlorine. Now look at oxygen. Oxygen में O2 molecule है. What is the structure of O2 molecule? Like what kind of bond is present between both the oxygen atoms?
Double.
Sorry, can you repeat that? Like what type of bond will you find in an oxygen molecule?
Double bond.
Double bond, right? Electronic configuration of oxygen.
1s2, 2s2, 2p4.
1s2, 2s2, 2p कितना?
4.
4.
2p4.
Yes. Let's ignore both of these because they're filled and focus on the 2p4 part of it. So this is the 2p orbital. 4 electrons are filled in this way. अभी ऑक्सीजन में कितने अनपेयर्ड इलेक्ट्रॉन्स हैं?
2.
2. So you have this and you have this, right? So let's give them names so that it's easy for you to associate it. Let's say this is px, this is py, and this is pz. Okay. Now oxygen atom 1, let's say this is the axis. पहला ऑक्सीजन एटम का न्यूक्लियस. Okay, so let's say this is the z axis. पहला ऑक्सीजन का pz orbital aligned along the z axis. दूसरा ऑक्सीजन का pz orbital aligned along the z axis. So the first bond is always a sigma overlap. Now, what about px and py? How are they arranged with respect to the z axis? Like if you had to visualize px, py, pz, how do they all exist in space generally?
Mutually perpendicular.
Mutually perpendicular, right? So they are like the 3 sides of the axis, 3 direction में. So अगर ये horizontal हमने z direction दिया, तो your py orbital will be perpendicular to it. And px orbital, imagine it's going like inside and outside the screen, 3rd direction. So this is the x direction, and ऊपर नीचे जो हो रहा है, like this direction is the y direction. So pz, the red color orbitals, you see that they're all along the axis, so that's a sigma overlap. The second bond that is there, py maybe there's unpaired electrons, right? So the py orbitals are going to undergo a pi overlap, ऊपर और नीचे इस तरह. Okay, so oxygen में you have 2 kinds of bonds. The first bond is a sigma pp overlap, and the second bond is a pi pp overlap. ठीक है? And z, like the third one, x px orbitals, they are completely filled up. They are not bothered with it. Like now all orbitals are happy, fully filled. Clear about this?
Yes.
Yes, ma'am.
Okay. Acha, let me know, like if in case you guys are noting it down or something, let me know if. Let me know once you're done. Okay.
Ma'am,
Yeah.
in VSEPR, if we have a double or a triple bond, then do we count that as one bond or two bonds, three bonds?
You in VSEPR you count it as a single bond.
Okay.
So that's what it's like when you have a double or a triple bond, that is considered as a single super bond.
Oh, okay. Okay.
So the reason is that you're looking at the shape of the molecule, right? So in order to figure out the shape of the molecule, you only need to know how many atoms it's bonded to. So for that, whether it's bonded as a single bond, double bond, triple bond, it does not matter as long as you have the correct number of atoms it's bonded to, because that's what's going to decide the shape, whether it's single, double, whatever it may be. Okay?
So it's just counted as one bond pair.
Yes. But one thing you need to be careful about, it will affect how many lone pairs the central atom has. So that part you need to be careful about. So once you have how many atoms it is bonded to and the number of lone pairs correctly, then you don't have to worry about whether it's a single or a double.
So like what are the type of questions that we can get based on VSEPR?
You'll just be given a molecule and then you'll just be asked what is like questions related to shape. Either what is the molecular geometry or what is the electron geometry or what is the bond angle between them. Like you'll be given a question like in carbon dioxide, what is the shape of the molecule? Or it could be assertion reason like in PCl5, the axial atoms are slightly longer than equatorial atoms. And then the reasoning ke liye you'll be given another statement. So you'll just be given certain molecules like SF6, PCl5, CO2, NH3, BF3, and then you'll be asked questions based on the shape.
And ma'am, how do we figure out the number of bond pairs and lone pairs in any given bond?
So that you will get from your knowledge of valency. So like for example, if you have BF3, valence shell में boron में कितने electrons है valence shell में? Like outermost shell में total कितने electrons?
3.
So boron का atomic number is
1s2, 2s2, 2p1.
5 है ना? So 1s2, 2s2, 2p1. You need to count second orbital में total कितने हैं? 2 plus 1, 3. Now the formula is BF3. So all 3 electrons are participating in bonding. So that's how you'll figure out कि अच्छा तो 3 bond pairs है और कोई भी lone pair नहीं है. Another
कोई भी lone pair नहीं है, that how do we figure out?
BF3, right?
Oh, there's 3.
Anyway, Kaveri, are you there?
Sorry, ma'am, I got a call. Yeah, I got it.
2, 3 है ना? और तीनों atoms fluorine के साथ bonded है. That's why you can say that there is no pair left at all. So there's no lone pair. Similarly, think of nitrogen, NH3. So nitrogen valence shell, like, और nitrogen का electronic configuration क्या है?
Valence.
1s2.
VSEPR में you don't have to worry about the atomic orbital तक जाने की जरूरत नहीं है. You can directly look at the 288 वाला configuration. So that way nitrogen, how many electrons are there in the valence shell total?
5.
5. No? So 5 में से how many atoms is it bonded to?
3.
3, right? And hydrogen is capable of forming like single bonds, double bonds, triple bonds. like what is the valency of hydrogen? How many bonds is it capable of forming?
Single bond.
Guys, hydrogen में कितने electrons होते हैं?
One.
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 So how many bonds is it capable of forming?
Single.
Single
Single
ही है ना?
bond.
Double bond तो नहीं कर सकता because hydrogen doesn't have those many electrons. So nitrogen, out of 5, 3 of them are bonded to hydrogen. So nitrogen has 3 bonded to hydrogen. Agar 3 electrons are occupied in bonding, how many are left on nitrogen?
2.
2.
2 are left, right? So now
One
you can
lone.
figure out, yeah. So 3 bond pairs and 1 lone pair. So that way, based on the valency, you can count how many bond pairs, how many lone pairs.
And ma'am, in this case, you saw like hydrogen was making, it could only make a single bond, but if it's like something more than hydrogen, which can make single or double or triple, how do we figure out what it's?
Based on the context, you can figure it out. Look at carbon dioxide. How many electrons on carbon?
4 in outermost.
4.
4, right? And अगर इसका valency खत्म होना है तो total कितने bonds बनाना है carbon को?
4.
4
4.
bonds. Lekin it is bonded to 2 oxygen atoms. So do you think carbon is bonded with single bonds or double bonds with the 2 oxygen atoms?
Double.
So 2 double bonds. So carbon has 2 double bonds. So based on the context, like these are all basics that you guys have studied. The central atom mein 1, check how many electrons are there. How many atoms is it bonded to? Is it CO2? Is it CO? Is it CO3? Kya ho raha hai? And based on that, you just have to distribute it so that sabka valency, like everybody has 8 electrons. That's basically it.
Ma'am,
Yeah.
in here, so in oxygen, carbon and oxygen, in that there are 2 double bonds, right? So in here, the first bond of both of the oxygen would be sigma bond.
Yes. The first bond, this is going to be a sigma, this is going to be sigma. And then the second bond is going to be pi. The second bond is going to be pi. Absolutely. Okay. Always, 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 the first overlap is always a sigma overlap. Okay, I don't need to. Okay, so this is oxygen. Should I go to the next part? Should I go to the triple bond part? You guys done with this?
Yes, ma'am.
Yes, ma'am.
Is it clear if I write it here or should I take it to the next page?
Either way is good.
If it fits over here, then yeah.
Okay. Figured like all of it will be in the same part page, right? That sounds right. Okay. The third one, nitrogen classic triple bond ke liye, let's go with nitrogen. Nitrogen ke electronic configuration, we just discussed 1s2, 2s2, 2p3. Isme the p orbital, all of them are half filled. So this, you guys only direct me. How do you think nitrogen ke bonds are formed? Nitrogen famously has a triple bond only. Okay, let me draw the axis. So this is the axis. As usual, this will be the Z axis. So let's have PZ in red, PY in blue, and PX in green.
Ma'am,
Huh?
I have like a silly doubt. If nitrogen has half filled, it's already stable. So why would it want to form bonds anyway?
Half filled is comparatively more stable than other like partially filled things, but fully filled is the topmost aim. So that's like the most stable. Octet configuration is what every atom is after. Okay.
So half filled is not as stable as fully filled. It's less
Yeah.
stable.
Definitely less. Octet configuration is like nirvana. That's the main aim of every single element atom there is. That's why noble gases don't bother with anything. They're just like chilling. But yeah, so if fully filled cannot be attained, then they settle for the next best things, which are like your half filled configurations and all of those other symmetrical things. Yeah. So nitrogen. So it wants octet configuration. It has 5 electrons. It's 3 short. So all 3 of them will participate in bonding to get 8 electrons. So again, as usual, first overlap. What is this kind of overlap called?
Sigma overlap.
Yes. Yeah. So this is a sigma pp overlap, like p orbitals of both the atoms are overlapping in a sigma way. Then y-axis में the blue orbitals overlap. So basically, these electron clouds are going to join together above and below. So technically, if you do like imaging studies and all that, it's gonna look something like this. So it is electron clouds upar or niche is taraf. It's not going to be like a clean p orbital shaped thing. It's going to be concentrated over here. Upar or niche. So this is pi pp overlap, pi py if you have to be like extremely specific. And in the third axis, imagine this coming outside the screen and going inside the screen in the third dimension. So again, this is also not along the axis. It's happening, if this is the axis, it's happening idhar or idhar, in front and like, if I turn it this way, it's going to look like it's above and below the axis. So this is the other pi overlap. Look like the electron cloud is concentrated over here. I don't know how clearly this is coming across, but are you able to visualize in a 3D way what's happening?
Yes.
A little bit.
Sort of, yeah.
So along the axis is this. Then the second one is upar or niche, idhar. And the third one is aage piche. Okay. So upar niche and then aage piche. So yeah, that's, so the first bond is the single bond sigma overlap. The second one is in one direction and the third one is in the other direction, X, Y, and Z directions. Okay. So this sort of overlap can be explained for like really simple molecules when there's just 2 atoms involved, like Cl2, O2, N2. H2 is like really easy. You have an S-S overlap in that case. Again, it's like a sigma overlap, sigma SS. If you take HCl also, H ka 1s electron and Cl ka the unpaired p electron. So it's a sp sigma overlap, all in the same axis. Sigma sp. Sigma sp. So it's a like single like molecules made up of 2 individual atoms unka bonding overlapping, you can explain it really easily. Okay.
Ma'am, I got disconnected after like you did the diagram of the third one. Could you please repeat once?
Oh no, I was just discussing like for simple molecules like H2, HCl, all the molecules made up of just two atoms, you can explain the bonding easily with the sort of overlap between S and P orbitals, right? Like hydrogen may you have sigma SS overlap, the S orbitals are overlapping. HCl may you have a sigma SP overlap, so S of hydrogen and P of chlorine are overlapping, and it's pretty straightforward, right? Now, can you try and apply the same thing to water, H2O? Okay, so let's take it, central atom is oxygen. Oxygen ka electronic configuration, you have 1s2, 2s2, 2p4. तो ये तो हमने पहले भी देखा है, like 2 of the electrons need bonding oxygen में. Hydrogen में it's just 1s1, so yeah, there's a single electron which is in need of bonding. It all seems pretty straightforward. Oxygen के 2 p orbitals है, so if I take oxygen atom central, एक p orbital in this axis and दूसरा p orbital perpendicular to it, then I can just like make it bond with hydrogen in each orbital. Sigma overlap हो जाएगा. This is hydrogen and this is oxygen. So in this case, what do you think is the bond angle between hydrogen, oxygen and hydrogen?
If 90 degrees.
90 आ रहा है ना? But based on VSEPR, what was the bond angle in hydrogen, in water?
Oh, 104.
So VSEPR is saying it's somewhere around 104 degrees. This is such a big difference, right? 14 degrees ka difference, not like 1-2 degrees. So why this difference? Which means that your VBT is not able to explain the bonding in slightly more complicated atoms, right? So how do you explain that? How do you come to terms with that? And VSEPR is a certified established theory. Like whatever VSEPR said, you could verify it experimentally and it all turned out to be correct. So VSEPR is correct. The bond angle in water should be 104 degrees gas pass. Why is that not happening with VBT, whatever sigma pi overlaps that we talked about? So what happens? So this model is wrong. Like this is not how bonding happens in water. One, we can say it is wrong because experimentally the results are not being matched. And two, again, VSEPR told us that fact already, right? Like if you have electron pairs, they will want to be as far away from each other as possible. So 90 degrees is just too close. Like it's not possible for them to exist this close, especially when there's other options. So this is explained by a thing called hybridization. Okay. So speaking of what is hybridization, when we talk about hybridization, have you guys come across the word hybrid before?
Yes, ma'am.
So what does hybrid mean? Where have you come across it?
I read somewhere that like a laptop was a hybrid laptop.
Hybrid laptop, what?
Yeah, like a laptop, like the touchscreen laptop thingy. Like,
Oh, okay.
yeah.
That's a very good example. So what do you think is the meaning of hybrid? Like what sort of idea do you get from it?
Like it's some sort of mutation or something that already exists, like half and half.
Very good. Half and half, right? So in this context, in chemistry ka context also, the word has the exact same meaning. Just apply it to atomic orbitals instead. Okay. So what hybridization theory, this particular theory tells us is, okay, like let's get some basics out of the way. So this was explained by Pauling. Like he was the one who used hybridization to explain the shapes of methane, water, ammonia, like these sort of molecules. Okay, slightly more complex molecules. So the point of hybridization is that atomic orbitals combine to form, so they combine to form a new set of orbitals. So what sort of orbitals are there? So they are equivalent orbitals that are called hybrid orbitals. And the sole purpose of this hybrid orbitals is that they are used in bonding. So whenever there's a question of covalent bonds, chemical bonds being formed, you basically, the atom only uses hybrid orbitals. And what type of hybrid orbitals are formed and what all atomic orbitals take part in combining, like all of that will depend on the context. So context in the sense, what all atomic orbitals are available and how many bonds does that atom need to form, like 2 bonds, 3 bonds, 4 bonds, 5 bonds, kitne bonds form karne hain. So depending on all of these contexts, the atomic orbitals of S and P that exist, they combine to form a new set of orbitals. So it's like, imagine you're putting the existing atomic orbitals, you're blending them up, and then you're redistributing them in like 4 different classes. It's kind of like that. So you get a new set of equivalent orbitals, and those new orbitals are called hybrid orbitals.
Ma'am,
Yeah.
I didn't get how this is different from VSEPR or VBT.
So VSEPR is giving you only the shape. So VSEPR just takes into picture, acha kitne lone pairs hai, kitne bond pairs hai, and based on that, it's just giving you the shape. Now, VBT and hybridization is explaining ki wo shape kaise aaya. So at the atomic level, what's going on? What's happening to the atomic orbitals? How is that shape coming into picture? Like, why is it a tetrahedron and not something else? Why is the bond angle 104 degrees or 109 degrees, but not any other angle? Why is it not 90 degrees? Why is it not 270 degrees? That way. Okay, so like think of it as individual bricks being laid out. Like VSEPR gave you the shape, VBT told you what's happening with the orbitals, ki kaise overlap ho raha and all that. And next, hybridization is putting both of them together. Acha, aisa orbit, like aisa overlap ho raha hai, and that is why you're getting the shape which VSEPR initially told you, like that. Okay.
Yes.
Cool. So hybridization ka definition, like if you want a word for word definition, so it is the process. Should I write it down or should I just like tell it.
Can you write it down?
Okay. So this is the definition of hybridization. Hybridization. The process of basically like forming hybrid orbitals. It's put in detail. So this is the process of intermixing of orbitals of slightly different energies. This word slightly is important. So it needs to be slightly different. Like a 1s orbital will not combine with a 3p orbital, but 3s and 3p can combine. 2s and 2p can combine. 2s and 3s will not combine. So it can't be extremely different. It needs to be just very slightly different. Slightly different energies so as to redistribute their energies resulting in the formation of a new set of orbitals of equivalent energies and shape. Okay. So hybridization, that's a process of intermixing of orbitals. That's how you're getting hybrid, right? Like different things mixed together to give you a hybrid of those things. And any random orbitals can't intermix. It needs to be of slightly different energies. Okay. And why is it getting intermixing? Why is that happening? So it's happening to redistribute their energies. So the eventual goal is to form a new set of orbitals. They all have the same energy and shape. So this also, I'll take a few examples so that it becomes clearer.
Ma'am,
Yeah.
when you say intermixing of orbitals, so you were doing the same thing now when it came to pi bonds and sigma bonds.
No. So sigma pi, that's their orbitals are not mixing. So that's just an overlap. Intermixing is basically you're disassembling them and reassembling them into completely new things. And second important thing, the sigma and pi are describing overlap. So there are two different atoms involved. In hybridization, whatever intermixing of orbitals is taking place, all of it is happening within the same atom only. Okay.
But like, what is the need for redistributing and all that?
Yeah, I'll give you an, like when we do examples, it becomes clearer. So there are some other like points about hybridization. So one is features. So the number of hybrid orbitals, like how many hybrid orbitals you get, is equal to the number of atomic orbitals. So if you mix 2 different atomic orbitals, you get 2 hybrid orbitals. If you mix 4 different atomic orbitals, you get 4 hybrid orbitals. So how many ever atomic orbitals you're mixing, you get those many number of hybrid orbitals. The second, the hybrid orbitals, I'll call it HO, are all equivalent in energy and shape. So basically they all have equal energies and they have like symmetrical, the same shape. The reason why hybrid orbitals are formed is hybrid orbitals are more effective in forming stable bonds. Compared to pure atomic orbitals. And fourth point, hybrid orbitals, they arrange themselves. This is the key point that leads to VSEPR. So they arrange themselves such that there's minimum repulsion in electron pairs. Okay. So like the features of hybridization is that how many ever atomic orbitals are going in, you get those many hybrid orbitals, those many are formed. Hybrid orbitals are equivalent in energy and shape. Even if you have different atomic orbitals, like even if you have S and P forming the hybrid, after hybridization is done, they all have equal energies, they all have the same shape. Atomic orbitals may have different energies, different shape, like S orbital is spherical, P orbital is that dumbbell shape. But once you've blended them together, once you've created the hybrid orbitals, they all have the same energy, same shape. And the main reason why hybridization is taking place is that hybrid orbitals are more effective in forming stable bonds. And the shape, the way these hybrid orbitals are arranged, they arrange themselves such that there is minimum repulsion in between the electron pairs. So basically, whatever is the type of hybridization, like whatever shape you get out of that hybridization, that basically decides the shape of the molecule itself. So that connects it to VSEPR. Like they both have electron pair repulsion wala part common between them. Here. Can I go to the next page?
Yes, ma'am.
Yes, ma'am.
Okay. Smira, Arnav?
Yes, ma'am. Done.
Yes, ma'am, done.
Okay. Cool. So conditions, so now let's get into how hybridization is taking place. So before we hybridize some orbitals, there are some conditions that need to be followed. So one, there should be valence shell ka orbitals. The inner orbitals are not going to take place in hybridization, bonding, anything at all. So whenever you're doing hybridization, it needs to be a valence shell orbital. Okay. Second, they should have almost equal energies. So that's what the slightly different part is about. They should have almost equal energies. So they should be close enough. You can't have an S and like the difference between the energy should be very, very similar. Okay. Next, promotion of electron is not essential prior to hybridization. So when we take up each case that I will talk about, and half filled only is not necessary. Like even fully filled orbitals can take part in hybridization. So promotion of electron is not necessary. And fourth is, it's not necessary that only half-filled electron orbitals take part in hybridization. So even fully filled orbitals can take part. Okay, so these are like the conditions.
Ma'am, I didn't get the third one.
Third one, I didn't elaborate on it. So when we come to that particular case, then I'll highlight it. So that
And the fourth one, why fully filled also take part?
yeah. So I'll tell you, like, so it's not necessary that it needs to be half filled. Fully filled in the sense we're talking about the valence shell orbitals only. Like if you have a configuration that's Px is fully filled, but Py, Pz are half filled, it's not necessary that this has to sit out. Like all three orbitals can take part. That's what the fourth part means. Yeah. All right. So first type of hybridization, let's look at sp hybridization. There should not be a hyphen between them. It's called sp hybridization. Hybridization, hybrid orbital names are also very, very, very logical, very easy. Can you take a random guess what all orbitals are taking part in hybridization just by looking at this?
S and P.
Yes, absolutely. So sp hybridization, you get sp hybrid orbitals when one s orbital and one p orbit. Okay, I don't mean this as 1s, 2s, wala 1s. Just one, like one number of s orbital and one number of p orbital. If you combine them, if you mix them, you're going to get sp hybrid orbitals. Can you predict how many sp hybrid orbitals you will get out of this?
One.
One.
Look at this point. The number of hybrid orbitals will be equal to the number of atomic orbitals. So if I'm taking one of s orbital and one of p orbital, total how many atomic orbitals have I taken?
Two.
Two.
Two
एक
atomic
s और एक p है ना? Yes. So this will give me 2 of sp hybrid orbitals. So the hybrid orbitals are called sp. Okay. So visually, if you had to look at it, s orbital एक जा रहा है spherical shape में, p orbital एक जा रहा है dumbbell shape में. You get 2 of the sp orbitals. So अगर दो orbitals को if you had to minimize the electron repulsion between them, how will you arrange them?
Perpendicular.
Perpendicular this way. एक orbital A से, एक orbital A से. You can still increase the angle, no? More than 90, you can linear. Just place them on opposite ends.
180.
180 degrees, yes. So this is one sp orbital and this is the other sp orbital. Okay. So there are two sp hybrid orbitals. Should
I didn't understand the figure. Like, what is the small one inside the big one?
inside nahi. So this is one sp orbital and the other one, like this is at the nucleus of the atom. So if I had to put them separately, they are like this. So there's two different sp orbitals. The way these two are arranged in an atom is agar ye nucleus hai, so one of them is over here and the other one, the second sp orbital, is at 180 degrees from this. It looks like this. Okay, so this is the first sp orbital, this is the second sp orbital. Like two sp orbitals are being formed and the way they are arranged in an atom is at 180 degrees from each other.
So that half dumbbell types, that is the figure for an sp orbital.
Yes.
Okay. And we don't, it's just like breaking it down and then arranging it again. So we don't need to pay
Absolutely.
attention.
Yeah. So it's just a mixture of S and P orbitals. Like orbitals are nothing but like they're basically blobs of electron cloud, right? So you imagine you're taking Play-Doh or modeling clay. One is a sphere and one is a dumbbell. You're just like mixing them all up together and then forming two equal things, hybrid orbitals. Okay, so this is hybrid of 1s and 1p. So this is the most ideal if the hybrids are on the same, like on z axis. Okay, so considering it is formed from one s orbital and one p orbital, how much of s character does it have? Like how much percent of s character and how much percentage of p character?
50-50?
Absolutely,
Half and half. No? So
half and half. So it has 50% S character and 50% P character. So equal parts of S and P. So it'll be equal part amounts of S character and P character. And geometry is linear. And I've shown you the shape also, how it is formed. So they're all aligned the same axis. Okay. An example of where you find SP hybridization, like this is important to note examples. Do you guys remember this compound called ethine or acetylene? Acetylene, also called ethine. How many of you remember this?
like the formula.
Formula, what is a compound? What is it made up of? Yeah.
C2H2.
C2H2.
Correct. Oh, nice. Some of you do remember it. C2H2. Do you remember the structure of C2H2? Have you
The
studied?
carbon bonds are the
Carbons have triple bond
Triple bond
and
and then
hydrogen on each
single
side.
bond with hydrogen.
Absolutely. Okay. So this thing. Okay. How do you figure what kind of hybridization is present? Is again, the first overlap is always a sigma overlap, right? How many sigma overlaps is each carbon undergoing? Like how many sigma overlaps are there for each carbon?
in total there are 3 sigma
No,
overlaps.
for each carbon.
For
2.
one there are 2.
2, right? इसका एक sigma है, इसका एक sigma है. Similarly, this carbon also 1 sigma here, 1 sigma here, right? So 2 sigma bonds, matlab it requires 2 hybrid orbitals to form this compound. So if you want only 2 hybrid orbitals, you need to put in 2 atomic orbitals. So that's how you can figure out that. अच्छा, तो इसके लिए 2 atomic orbitals, so 2 hybrid orbitals form करना है, मतलब it's going to undergo sp hybridization. Okay. So how does the hybridization take place? Is let's start with carbon, क्योंकि that's the central atom here. Carbon का atomic electronic configuration क्या होगा?
2,4.
2,4. Now, because we're talking about hybridization, sp and all that, expanded form.
1s2, 2s2, 2p2.
2p2.
2p2, right? So you have 2 s electrons over here and p electrons, 2 of the p orbitals are filled here. Okay. Now, sp hybridization. So before undergoing hybridization, so you can see that carbon needs to form 2 sigma bonds and 2 pi bonds. Okay. So pi bonds, like only the p orbitals are capable of forming pi bonds. So that means that the electrons, like 2 p orbital में 2 electrons होना चाहिए And ये दो sigma bonds होने के लिए भी the electron needs to be completely distributed. So this is the ground state configuration. This is like the natural state. Then one of the electrons is excited to this particular orbital. So excitation takes place. So one electron jumps here. So the excited state configuration is going to look like this. So all the electrons are uniformly distributed between all the orbitals. So this is the excited state configuration.
How do we know there's going to be excitation?
Again, I told you, right? Like carbon needs to form 4 different bonds, like 2 pi bond chahiye or 2 sigma bond chahiye, which means that the 4 electron needs to be in, like all the 4 electrons need to be in 4 different orbitals. So ek khali, like you can't have an empty orbital participating in bonding, like it needs to contribute an electron. So that is the reason you can figure that achha, maybe this is also going to take part in bonding. So 1 electron needs to go here. So this S se P tak ja raha hai na. So this is called promotion of electron.
Does promotion of electron happen in all like bonds that we need to show hybridization, or is it just?
That's what the third point says. So promotion is not necessary for hybridization. Wherever it is required, it will happen. But if this particular orbital is not required, it's just going to be empty without anything, then promotion will not take place. So it's all need based, depending on the context. Promotion chahiye hoga, to fir excitation, like wo promotion hoga. Otherwise, when it is not necessary, it will not take place. So hybridization ke liye compulsory.
I didn't get when, like how we know if it's necessary or not. Could you explain that again?
There is no theory behind it. So basically, the more examples we do, the more you'll come to know of the context behind it. So like I just mentioned, right? Like carbon needs to form all 4 bonds. Like the 2 p orbitals are going to take part in pi bonding, and then electrons need to be there in other 2 orbitals also, which means that every single orbital over here needs to have an electron in it in order to be able to take part in bonding. So that's why we see that there's an empty orbital here. This cannot be empty. Then we say that acha promotion will take place. But there are other cases, like we'll come across situations when promotion is not necessary also.
So like in this case, carbon has to form 4 bonds. So that's why all 4 of them have to be in different valence shells.
Correct. So all 4 orbitals need to have a single electron in them. So now they're ready for bonding, get another electron in them. Yeah. So if you come across a situation where that is not necessary, then excitation will not take place. Okay, so this is the excited state. Here also it's there as, individual S and P electrons. Then hybridization will take place. So 1 s and 1 p orbital will give rise to 2 sp orbitals, hybrid orbitals. So now after hybridization, carbon has 2 equal energy sp orbitals. So this is after hybridization. So each has like a single electron in them. And only because 1s and 1 of the p orbitals has taken place, the other 2 are going to remain as it is. So the other 2 p orbitals will remain as it is. So px, py will remain as it is. We call them px, py.
So if we say sp, it means 1s and 1p. That's it.
Correct. Just 1s and 1p. Yeah. So this 1 doesn't stand like this. 1 is not this. We're just indicating how many s orbitals are there. Yeah. So now this is ready for bonding. So what happens is, let's say we have one carbon here, one carbon here. The sp orbitals are arranged linearly. They're even, okay, like I drew it wrong, but imagine them to be even. So दूसरा carbon में भी this will also undergo the same process. तो इसका भी दो sp orbitals रहेंगे. So these will have a sigma overlap. Now individual, like each of these carbons will overlap with hydrogen. This is hydrogen. इसका ये दूसरा hydrogen है. Again, this is a sigma overlap. Then यहाँ पे, so the sp orbitals have done their part. They have bonded. Now the remaining other two p orbitals are there, right? So they are again perpendicular to the axis. So they will do their job of forming the pi overlaps. So this is the second bond and this is the third bond. Okay. So if I have to highlight it, the sigma overlap is the first bond and the second and third bond are your pi overlaps. This is kind of basically how hybridization works. So it's all convenient.
Ma'am,
Yeah.
could you explain just the sp part again? Just the
What do you mean
two-
sp part? Like
I got how hydrogen were bonded and the px and py were bonded. I didn't understand the sp, the 1s plus 1p, that part.
that's hybridization, no? So
Yeah.
हर एक carbon में
What-
एक this one single s orbital and one of these three p orbitals. So one s and one p, the ones that I've highlighted, these two are going to combine and then form two different sp hybrid orbitals. So because they are hybrid of s and p, we call them sp hybrid orbitals. They are equal in energy. And yeah, so they each again have like a single electron within them. So ये red color में जो है, those are your sp hybrid orbitals. अभी इस carbon के पास दो sp है ना. So one of the sp orbitals will bond with hydrogen and the other one will bond with the other carbon. So इसका एक sp orbital has overlapped with this hydrogen and दूसरा sp orbital जो है वो दूसरे कार्बन के साथ overlap किया. So the other two p orbitals have remained as it is and they have formed the pi overlap.
So the dumbbell shape inside of which there's a small dumbbell shape that makes for one sp orbital. Sorry, that makes for one sp hybridization.
Inside nahi. This is one hybrid sp orbital and this is the other hybrid sp orbital. I've just put these two together. So I took this and put it over here. That's why it looks like one is inside the other. That's basically it.
So that is two, right? So दूसरा वाला कहाँ से आया?
There are two sp formed, right? Because you're putting in two atomic orbitals, you need to get two hybrid orbitals. So पहला वाला है, ये वाला is the first one. And this is the second one. That way.
Oh, and like that there are two carbons, so then we get
Correct.
together.
Yeah.
Acha, okay. Got it. Can we be asked to like draw this or just
You're getting MCQ type. Maximum, you might need to identify if a diagram is already given. If you had wait, you have a subjective component also, right? 20 marks ke liye.
Yeah.
Then you might be asked to draw. Yeah.
Okay.
Okay. Clear? Hybridization is nothing but intermixing of atomic orbitals. Now we are looking at each individual case. Like the first case we are looking at is if I take one s and one p orbital and if I mix them, what will I get? And this is an example of where you'll find this kind of hybridization. ठीक है? All of you being like really quiet except Kaveri.
I think I got it. Yeah, I understood.
Okay. Like your camera is also off, so I don't know. I don't really know where you guys are at. Like, are you understanding? Are you not? Are you like busy noting it down? Kya ho raha hai?
I'm noting it down.
Okay.
Drawing the figure.
Yes, ma'am, drawing.
If there's any part that you did not understand, you have to let me know. Okay.
Ma'am,
Yeah.
when we say 1s and 1p orbital,
Hmm.
so in any element, if we see,
Hmm.
there will only be one s, I mean, only one s orbital, right?
I've been telling that so many times. This one is different from this one. This is, I'm calling it.
No, I'm not. I got it. It's I know you're telling like it's one of the s orbital. I agree.
Yes.
I understand.
Huh.
But I'm telling for any element, it will be only one only, right? There can't be more than. Oh wait, s, right? Then for each time there is an s orbital, it will add up, right?
Yeah.
Okay.
I mean, it depends on the situation. Like that's what hybridization says. It's not fixed कि हमेशा sp होगा. Like in this case, दो atom के साथ bond करना था. That's why carbon had requirement of just I need 2 hybrid orbitals. So अगर 3 atom के साथ ऐसे bond करना है, then carbon is going to be like I need 3 hybrid orbitals. So get to work based on that. And if carbon needs to form all 4 bonds, then it's going like it needs 4 of the hybrid orbitals. So that hybridization is going to be different. So it depends on the requirement, like what the situation is. Okay, so we will look at each of these cases. Yeah. So let me know when you guys are ready, then I'll go to the next case. Okay, Arnav is done.
Ma'am, done.
Avi is done. Rishit?
Yes, ma'am.
Okay. So next one, we're going to talk about sp2 hybridization. Now you guys only lead this. So tell me sp2 कैसे मिलेगा मुझे? In the previous case, we saw sp, we had one s and one p. sp2 के लिए क्या चाहिए?
One less than 2p.
2p.
Absolutely. So one s and wrong placement of brackets. So one s and two of the p orbitals will give me total. How many sp2 hybrid orbitals will I get?
3.
3.
3 sp. So this needs to be sp2. 3 sp2 orbitals because I'm taking 3 atomic orbitals total. Equal numbers आना चाहिए. Okay. So visually you have spherical s orbital and 2 of the p orbitals. So if this is the axis, one is this way, the other one is perpendicular to it. So these three will combine. So I'll get 3 identical sp2 hybrid orbitals. And the way they are arranged, so if you had to arrange all of these 3 in a symmetrical way to minimize electron repulsion, what shape will they take?
Triangular.
Triangular pyramid.
What is the technical term for it?
Trigonal planar.
Diagonal planar.
Diagonal planar.
Trigonal planar is correct. Okay, so one will be like this. The second one will be at 120 degrees, and the third one will be at another 120 degrees. Okay, so the geometry is trigonal planar. So again, just like we discussed for sp, how much is the percentage s character in this? And how much percentage is p character? So what ratio of this hybrid is made of s and what ratio is made of p? This is a simple math question, you guys. Batao.
So 33% of S and 66 of P.
Absolutely. So 1/3. So that's like 33.3% of S and 66. 2/3 will be the P character. This is 1/3 S character and 2/3 P character. Simple. Total 3 orbital mil rahe. So 1 out of the 3 you're taking S and 2 out of the 3 you're taking P. Everything is conserved. So hybrid orbitals maybe if you take each one, partly S and partly P. 1/3 is S character, 2/3 is P character. Okay. Examples would be BF3, BCl3. So these like boron will undergo sp2 hybridization and slightly more complicated in comparison to ethylene. Acetylene. Do you guys remember this compound called ethylene? Also called ethene.
C2H4.
C2H4.
Correct. C2H4. Okay, so in this carbon undergoes sp2 hybridization. How do you figure that it's sp2 hybridization? I'll just draw it freshly here. Okay.
So, ma'am, in this case, there was no excitation or anything.
We'll look at that. I don't know that yet. Basically, it's C2H4, right? So carbon, like what will be the structure of this? I have 2 carbons here. Single bonds, double bonds, triple bonds, kaisa?
Double bond.
Double bond.
Double bond. And how are the hydrogens arranged?
2 with each carbon.
2 single bond to each carbon.
2 single bond.
Correct. 2 for each carbon. Okay. So this is ethylene. So each carbon needs to form how many bonds? If I take this carbon, कितने bonds form, like कितने sigma overlaps हो रहा है इस carbon के लिए?
3 sigma overlaps.
3 sigma overlaps, right? मतलब 3 hybrid orbital चाहिए इसको. So again, as usual, carbon is 1s2, 2s2, 2p2. So this S, and you have this P. Okay, now it needs to form 3 hybrid orbitals, but basically it's forming 3 sigma and 1 pi. So now you tell me, is excitation required in this?
Yes.
Yes, excitation is required because again, like all the electrons need to be distributed. So this electron gets excited over here. So this is ground state. And after excitation, it's all like the same story keeps repeating.
Ma'am,
Yeah.
what if there isn't enough space for all the electrons to be equally distributed? Like if there's 2 in S and then 5 in P, so there won't be equal distribution, right?
There won't be, and it'll be limited by, like, again, that's the reason it depends on the context. So if P was completely filled, then if there were 5 in P, there's only one more electron that is required. So in that case, hybridization is not necessary. It just can form like a single overlap, like in the case of HCl. HCl में क्या हो रहा है? Cl is P5, right? So that single P electron that requires the electron, that requires that 6th electron, is only going to take part in bonding. उसके लिए कोई
And
hybrid
what if there's 4 in P?
नहीं होगा. Huh?
What if there is 4 in P?
Even if there's 4 in P, again, it completely depends on the context. So we will discuss hybridization in water also. So that should clarify it. That will show you a case where that is the thing. Okay. Okay, let's focus on this right now. So ground state for excited state. Because there's 3 sigma overlaps, we need 3 hybrid orbitals. So S and the 2 p orbitals will give 3 sp2 hybrid orbitals. So this is what it looks like. So you have 3 sp2 hybrid orbitals, all of them equal in energy. They each have single unpaired electron, and there is one remaining p orbital unchanged. So now carbon 1, the 3 sp2 hybrid orbitals arrange themselves in a triangular way. This is one. This is another.
Ma'am,
Yeah.
how did we figure out that there's 1 S and 2 P? Because if it's equally distributed anyway, then how do we know?
No, because there are 3 sp2 hybrid orbitals formed, right? That's why we know that there's 1 S and 2 P.
I didn't get it. What?
Like you asked, how do we know that it's 1 S and 2 P, right?
Yeah.
So there are 3 sp2 hybrid orbitals, which means that 3 atomic orbitals need to take part. So S to ek hi hai, and 2 of the p orbitals. That's why it's like 1 of the S and 2 of the p.
And then what about the last one? That will not.
Yeah, I've written it here, right? So that's unchanged.
Yeah.
Okay. It's like this. The other one's like this. And then the third one's like this. फिर दूसरा कार्बन का भी the same thing will happen and those two will overlap. One here, and one here. Now, the other sp2 are like overlapping with the 1s of hydrogen. So these two are carbon, this is the next carbon. Now the single p orbital that's there, put that in a different color. So this p orbital is perpendicular to the plane. So आगे पीछे रहेगा. And that will form the pi overlap above and below this plane. This is like the pi overlap. So these are the sigma overlaps. यहाँ पे जो है. This is the pi overlap. So the triangular planar is on this plane. So the p orbitals are overlapping above and below this. So यहाँ पे that the double bond, the pi overlap is happening above each other. Here you have the sigma overlap. Like the hydrogens are also in this plane, the carbons are also in this plane, all of them are in this plane. Only the p orbitals, the double bond wala part is above and below. So, like there is a 3D thing I can show you guys here. Ethane. Oh, nicely given here. So you have 1s, then px, py, and pz. sp2 ke liye one of the 2s orbital and two of the 2p orbitals will give you 3 sp2 hybrid orbitals. They're all in the same plane. And the pz is unchanged. And you can see it is perpendicular to this, like you're looking at this view over here. And the triangular planar is in the same plane, the green part of it in this plane. And the pi bond is above and below the plane. So you can see this is the sp2, this thing. You can see sp2 orbitals, all of them are in the same plane. And showing the remaining p orbitals, upar or niche they're aligned here. And resulting pi orbital. So this mesh shows you how the pi bond is. So the sp2 orbitals, the yellow bonds are all in the same plane. And iske upar or niche you have the pi orbitals. This is the ethene molecule. Is this clear? Does this make sense visually at least?
Yes.
Yes.
Yes, ma'am.
Okay. You guys can like go to this website and play on your own. Makes sense. It's called ChemCube 3D. I'll ping this link. Acetylene भी देख लेते हैं. So sp is linear this way. The overlap is also shown here. Oh, this has just ballooned up, but yeah. So you can see the pi overlap in like, yeah, it's a linear shape thing. Anyway, okay. So other molecules that you find sp2 overlap is in, or कौन से molecule has a trigonal shape? I told you guys, I'd shown this to you previous thing, right? So BF3, BCl3 also you find this particular hybridization. So this is ethene molecule, also called ethylene. Yeah. Should we go to the next hybridization, next example?
2 minutes, ma'am.
Okay. Okay, Smira, Arnav are done. Okay, Ritu, Kaveri, Rishit, and Adir. Oh, cool. Everyone's done. Okay. The next one, again, very predictable. Can you guess what the next type of hybridization is? We've been through SP. We've been through SP.
SP3.
SP3, correct. This is like the most commonly found, and this is like really easy. So how do you get sp3 hybrid orbitals?
1s and 3p.
Yes, 1s orbital and all 3p orbitals. Combine them to get, how many sp3 hybrid orbitals do you get?
4.
4.
And if you had to arrange 4 hybrid orbitals in a perfectly symmetrical way, what is the shape? Tetrahedral shape, yes. So anything with a tetrahedral electron geometry, you can blindly say that, oh, it's undergoing sp3 hybridization. Okay. Again, like basic characteristics, like how much percentage S character does it have?
25%.
And the 3 P's will be 75.
Absolutely. So 25% S and 75% P character. So 1/4 and 3/4. Okay. So examples for this, going with the pattern, methane, CH4. So it's pretty simple. You have carbon requires 4 bonds. So bond it to all 4 sides with hydrogen. So methane will undergo sp3 hybridization. That is why the shape of methane molecule is tetrahedral. So same, the exact same logic, exact same pattern. So carbon has 1s2, 2s2, 2p2. So sorry. Here also the promotion will take place as usual. Excited state. So excited state configuration will have all 4 unpaired electrons. And after hybridization, you will have 4 equivalent sp3 hybrid orbitals. Okay, and all 4 of them perfectly symmetrical tetrahedral shape. Okay, and each of them is bonded to different hydrogen atom. All of it is sigma overlap. So this is central atom carbon, and each of these is hydrogen. Yeah. So this is like the easy example, like since we discussed acetylene and ethylene, like ethyne and ethene, logical pattern like carbon, the single bond compound of carbon is methane. So we'll discuss the structure of methane. Yeah. Let me know when you guys, yeah.
Could you just go to the previous slide for a minute? I just missed one thing.
Yeah.
Okay.
Ma'am,
Yeah.
I'm still a little confused about how to identify if it's sp or sp2 or sp3.
It depends on how many hybrid orbitals you require. Okay. So I'll just put all the compounds side by side for comparison. So that will be easy for you to check also. Okay. So we saw ethyne first, which was basically had the structure, right? And then we saw ethene next, which was C2H4, looked like this. And then we saw methane, right? 4 bonds of carbon. Okay. Now, how many sigma overlaps did each carbon, like focus on only one carbon atom in each of these cases. How many sigma overlaps did this carbon need? Like how many different atoms did it need to bond with?
How many sigma bonds or how many bonds?
Like
4.
think of how many atoms did this carbon need to bond with?
2.
2. It bonded with one hydrogen and it bonded with the other carbon, right? So दो bond किया, like 2 atoms के साथ bond किया. Now the double and triple bond are going to be pi bonds. That's why we are ignoring them for now. We're just looking at the sigma overlaps here. So 2 atom के साथ bond किया, मतलब कितने hybrid orbitals चाहिए थे इस carbon को? It bonded with 2 different atoms. So how many hybrid orbitals will this carbon need? What happened? Like 2 bond के लिए how many orbitals? 2 orbitals चाहिए, 3 orbitals चाहिए? Kaveri, are you there?
Yes, ma'am.
हाँ, तो अगर दो एटम के साथ बॉन्ड करना पड़ा तो how many orbitals will this carbon need?
I don't know.
So एक बॉन्ड के लिए एक ऑर्बिटल चाहिए. So दो बॉन्ड के लिए दो ऑर्बिटल.
Okay.
अगर तीन बॉन्ड बना रहा है तो तीन ऑर्बिटल्स.
Okay.
Yeah. So
Okay.
this carbon bonded with two different atoms. So it required two hybrid orbitals. And two hybrid orbitals matlab, in which case do you get only two hybrid orbitals?
SP.
SP, because you're taking only two atomic orbitals. So
Okay.
in this case, you can see that each carbon or a particular carbon is bonding with three different atoms. So one hydrogen, second hydrogen, and the third carbon, right? So this is one, this is two, this is three. So agar तीन bond बना रहा है, तो how many hybrid orbitals would it need?
SP2, like 3 hybrid orbitals.
Yeah, it needs three orbitals. So it's going to get three orbitals if it does sp2 hybridization. In methane, how many different atoms is this carbon bonded to?
4.
So how many orbitals would it need?
4.
So which type of hybridization?
SP3.
Yes, 4 hybrid orbitals matlab you'll get it from sp3 hybridization. So that's how you figure it out. So I'll give you one more compound. This time I'm not going to ask any leading questions. Figure it out and tell me, okay? So formaldehyde. So formaldehyde is the chemical that you use for preserving dead things, like biolab mein whatever specimens you have that pungent smell, right? So formaldehyde is the compound that is used for the preservation. The formula of formaldehyde is HCHO, and the structure is central atom carbon. It has double bond with oxygen, and the other two are bonded with hydrogen. So can you guess what is the hybridization of this carbon in this compound?
SP3.
Why?
Sorry, it's 3 sigma, SP2.
There you go. That's it. Okay. Now, anybody, like all of you actually send the answer over chat. PCl5. So this in VSEPR, you've already seen the structure. P is the central atom, and this forms 5 single bonds with chlorine. Actually, no, like not yet. We haven't come across this type of hybridization yet, so not yet. Let it be. Okay. So once you guys are done noting down the methane ka part, we'll discuss a few more examples of sp3, and then we'll talk about PCl5 and SF6 also, what sort of hybridization you get.
Can there be a hybridization sp3d or something like that?
Yes, absolutely, you're right. PCl5 undergoes sp3d hybridization. So the d orbital also gets in the mix.
How many such are there hybridization types?
So list of hybridization, like you have sp, sp2, sp3. So these are only purely between s and p. With d orbitals, you have sp3d, you have dsp2, you have sp3d2. What else? d2sp3 also, I think. Yeah, I'll put it in a logical order. So you have sp3d, 4, 5, sp3d2, this is 6. Then you have dsp2, and you have d2sp3. Yeah, so these are all the different hybridizations that you have. So depending on how many bonds that particular central atom is forming, it's going to pick which is the most suitable hybridization there is. So anyway, let's discuss PCl5 anyway, because you have this. So phosphorus
I
pentachloride.
had a doubt, like kind of confusion, but we only consider when we choose if it is sp2, sp and all, we
Mhm.
only check the sigma bond, not the pi one.
No, only the sigma bonds. Because pi bonds, only p orbital is capable of forming. And the condition for pi bond is that it needs to be perpendicular to the axis where the nuclei are there. So whenever there is a question of pi bond being formed, some p orbitals are going to remain as they are. They're not going to take part in hybridization. You consider only the sigma overlaps. Okay, PCl5 में you have, like I've given the whole list of different types of hybridization here. What do you think is the hybridization taking place in PCl5?
sp3d.
SPD is absolutely right. So the examples we discussed earlier, like carbon, nitrogen, oxygen, those will only go until 2s2p, right? उनके पास d orbitals नहीं है, तो उनमें you won't find that hybridization. But in the case of sulfur, phosphorus, and the d block elements, you'll find all these, this expanded octet configuration के लिए, you'll find all of this configuration. So PCl5, it is undergoing, it has like 5 different atoms it is bonded to. It needs 5 of the hybrid orbitals. So it's going to undergo sp3d hybridization. Okay. So based on that, sp3d ka shape, can you tell me what is the shape of sp3d? You just have to figure out what is the shape of phosphorus pentachloride.
Trigonal bipyramidal.
Yes. So you have trigonal, triangle in the same plane in the center, and 2 pyramids, upar or niche, so bipyramidal. sp3d2 का shape क्या होगा?
Octahedral.
Octahedral is right. sp3d2, you have total 6 hybrid orbitals, right? So if you had to arrange 6 bonds, yes, square in the center, upar niche perpendicular, so you get octahedral. So dsp2 is slightly different. Even though it has 4 hybrid orbitals, the cases where dsp2 is formed is different from the situations where sp3 is formed. So iska shape is square planar. So all the dsp2 hybrid orbitals are located in the same plane, like I said, diagonally. And the remaining p orbital is basically there perpendicular to it. So that's how dsp2 is. And d2sp3 again is octahedral. Yeah. So yeah, this is all about hybridization. Beyond this, there is only practice. Like you pick each different type of compound and then figure out what sort of hybridization is there. And once you figure out the hybridization, everything else falls into place. You can figure out what is the shape of the molecule, angle between, and all of these other things. What type of overlap. Okay, so just note it down, revise everything there is with hybridization. I'll just get some questions and I'll just be right back. Yeah. Are you guys ready for questions?
Based on hybridization?
Yeah.
You mentioned D2SP3. Oh, that's the same. Okay, that's the same. Sorry.
Ma'am, just 1 second. I'm on like the second last one. I'm copying it down.
Okay, whenever you're ready, let me know when you're ready and then we'll start.
Ma'am, could you also write the shapes of SP, SP2, SP3 once again?
SP, you tell me what do you think is the shape of SP? अगर दो ही है orbitals, तो how will you arrange both of those?
Will it be linear?
Correct. SP2, तो 3 है, तो 3 को कैसे अरेंज करोगे?
Will it be trigonal or something like that?
Trigonal, yes. Planar or pyramidal?
Then it will be planar.
Planar, yes. And SP3, I get 4 hybrid orbitals. So how will I arrange all 4 of them?
Tetrahedral?
Tetrahedral is right. You know all of these.
Ma'am, the DSP2 and D2SP3, are those in the textbook? So I can't find it.
I don't know, but like there are cases where you will come across these at some point or the other. Just
Okay.
keep it there, like good to know sort of a thing. Just keep it there. And I found a lot of questions that include these, like among options or something. You are going to keep revisiting hybridization in a lot of other chapters. Just like your electronic configuration, this is like one of the basics. So when we do organic chemistry, hybridization matters a lot. It decides the shape of the organic compounds, which in turn decides like the stability and the boiling point and density and all of these other things. Even coordinate compounds like D block elements form special kinds of coordinate compounds. So unka shape is decided by what sort of hybridization they undergo. Like atomic structure and your chemical, like molecular structure, are your basic building blocks. that will help you figure out the rest of the big thing, physical properties, chemical properties, all of that stuff. So we like get this out of the way right at the beginning. And by the end of 11th standard, you'll find these are like the easiest chapters because you will keep using the concepts again and again and again.
Ma'am, I had a question.
Yeah.
Is methanol and formaldehyde, which you gave in the last example, are they the same?
They are
Because
correct. Same thing, correct. Methanol is the IUPAC name and formaldehyde is the common name.
Oh, okay.
Yeah, it's an aldehyde.
I'm done.
Okay. So Adit is done. Ritu, Arnav, Smira, Kaveri, Rishit, you guys ready for questions? Rishit is ready. Ritu is okay. Awesome. All right, so I'll give you a bunch of compounds and then you tell me what kind of hybridization they would undergo. First one is methane. Or put it on chat because I want all of you guys to answer it.
What do we have to do?
Give me the type of hybridization. With SP, SP2, SP3 or SP3D, SP3D2. Yes, Adit got it. I'll give all of the compounds. You guys can send. Smera got the first one. Kaveri got it. Arnav got it. Kaveri got the second one. Yes. Ritu and Rishit, first one I'm assuming. Yeah. Smera, correct. Adit, like one, if there is number one, you don't have to mention it. It's like algebra में जैसे 1 into x को x ही बोलते हैं ना? Same concept. Arnav, correct. Rishit, correct. Smera got the third one. Kaveri got the third one. Arnav got the third one. Adit got the third one. Rishit, put the number, no, it'll be clearer. I don't know which one you're on. Rishit, is that, you sent me the second one, right? Yeah, then the third one is right. Smera got the fourth one. The two second one correct. Kaveri got the fourth. Arnav got the fourth. Because all of you have gotten it. Yeah, this is SP3 is correct. This SP is correct. Ritu, yes, third is correct. Rishit, yes, got the fourth. So this SP2 is correct. This I'm waiting for a couple of you. Adit, yes, fourth is correct. Sabka ho gaya? This is SP is correct. Awesome. Nice. So now you can identify what sort of hybridization. I'll give a slightly bigger compound. Logic is the same. No. The logic is the exact same. So don't get stumped by it, okay? So this is an organic compound. So you have CH2, double bond, CH, single bond, C, triple bond, C. Sorry, C nahi hai last one. This is triple bonded to nitrogen. So this is carbon number 1, carbon number 2, carbon number 3, let's say. What is the hybridization? Like you can answer it as SP, SP2, SP3, whatever. Like तीनों एक ही line में, just separate it with a comma and answer it in this order only. Like first carbon, second carbon, third carbon. If you mix it up, I am going to mistake it in different way. So to be clear, pehla wala, whatever you send is going to be for this. The second one will be for this carbon. The third one will be for this carbon. So what is the hybridization for each carbon? So send your answer in this format. You may or may not use brackets, but separate it out with a comma and send the 3 answers. If it's still kind of new for you, you can write the expanded format. So you can write this as carbon here, फिर double bond carbon. This is attached to 2H. ये double bond के बाद, this is attached to an H and another carbon, and this is attached to a triple bond nitrogen. So I've given you the expanded format also. It's the first carbon, the second carbon is the third. Don't send it separately. Like, give all 3 of them, separate them with a comma and send it in a single line. It'll be convenient. Otherwise, keeping track will be difficult. Rishit sent it. And Rishit, you absolutely got it. Good job. You said. Kaveri, your first carbon ke liye it's right. Send all 3 of them together. Smira also got it. Good stuff. Yeah, Rishit. Yes. Come back. Kaveri, you got all 3 of them. Absolutely. So I'm waiting for Ritu, Arnav, and Adit. Arnav, 4 कैसे मिले? There are only 3 carbons here. This one, and this one. What is the 4th one? Send the answer again. Ritu and Adit, are you guys working it out? Are you stuck somewhere? Are you getting it? Yeah,
I'm trying to figure it out.
Okay. Whatever you did for the first thing, you guys answered it all correctly. You need to do the same thing. To make it easier, take it 1 carbon at a time. Yeah. Use the same logic. And use this as a hint. I've given the expanded format.
I didn't hear what you do.
Arnav got the right answer. Yes, Kaveri, what's up?
Do we have to do something else? Like what?
Yeah, if you're sitting, I can give you the next question. Okay. Do you know of the word, what do you mean by isostructural? Actually, again, this is like a new type of question, right? So we'll discuss that once the others are also done.
Is it having the same structure?
Oh, here, yes, isostructural is same structure, but hold on to that. We're not discussing that yet. Okay. Identify the structure for, like, let's hybridize it, like same thing, continue. Use BRF5. So in this case, you need to tell me what is the hybridization, not the molecule wala shape. So rest of you work on this. Adit, where are you at? What's happening?
What do we have to do for BRFI?
Figure out the hybridization. Okay, so Ritu, take it one carbon at a time. Look at the first carbon. Look at the expanded form, first carbon, ye wala carbon ka. How many other things is it bonded to, this carbon?
2 other things.
Kaise? What all is it bonded to? This is 1.
2 hydrogen and 1 carbon.
That's a total of how many atoms is it bonded to?
3.
3. So if it's bonded to 3 things, what hybridization would it require?
sp3.
sp3 say you're getting 4 hybrid orbitals. No, it just requires
sp2.
sp2. So the second carbon, consider this. How many different things is this one bonded to?
3 different things.
Yeah. So 1 carbon, the second carbon, and this hydrogen. So what will be the hybridization for this?
sp2.
sp2 again. Yep. And this third one?
Bonded to 2 other things.
Yes. So this carbon and the nitrogen. So what will be the hybridization for this?
sp.
sp. Absolutely. That's it. That's all there is to it. Okay.
Ma'am, in BR5, boron only has like, sorry, it's not boron.
Yeah, this is bromine. Do you guys know how many valence electrons bromine has?
5.
5.
No. Rishit, Kaveri, what
Is
about
it 2?
No.
I just know the atomic number. I don't know valence.
Whoa. You guys have studied periodic classification. No?
7.
7 is right. Kaveri got it right. So bromine belongs to the same family as fluorine
Fluorine.
and iodine. So just like fluorine and chlorine, it has 7 valence electrons. And out of these 7, how many are taking part in bonding?
5.
5.
Right? So 5 are bonded to fluorines. All single bonds because fluorine is single bond. So that is a total of how many electron pairs?
Five.
Correct?
5 bond pairs and 1 lone pair.
Correct. So you have 5 bond pairs and 1 lone pair. So total 6 electron pairs, matlab, how many orbitals would be formed?
2.
Though orbitals can accommodate like 6 electron pairs. You have 6 electron pairs, 1, 2, 3,
6
4,
orbitals for
6
6.
orbitals.
6 orbitals. Smera already figured it out. She sent the answer. So 6 orbitals matlab kaun sa configuration, I mean kaun sa hybridization chahiye hoga bromine ke liye?
D2sp3.
Good guess, but bromine will undergo sp3d2. Arnav also sent it absolutely right. So Br, if I may, the hybridization is sp3d2. So the difference between d2sp3 and sp3d2 is, so like, let me take electronic configuration, okay? So you have 1s, then 2s, 2p, 3s, 3p, then 3d, then 4s, 4p, 4d. Let's say it keeps going on, right? Now, if you take, like, if the hybridization is involving पिछले shell का d orbital and your s and p orbitals, then you get dsp2 or d2sp3 depending on how many orbitals are taking part. But if hybridization में, if the same shell के sp and d orbitals are taking part, then you get sp3d2 and sp3d hybridization. Okay, so difference between d2sp3 sp3d2 is basically which specific d orbital is taking part in the hybridization. So agar same shell ka sp3 orbitals, all the orbitals are belonging to the same shell, then you get sp3d2 and sp3d. But if the d orbital, if you're taking it from the previous shell thing, your s and p are in the fourth shell, but instead of 4d, if you're taking 3d, then you get your dsp2 and d2sp3. Okay, so that's the only difference between these two hybridization. You'll find these mainly in D block elements. Your P block elements are going to prefer sp3d to sp3d because they have either completely empty D shells or they have completely full D shells. So it's not going to be bothered. But your D block elements have incomplete 3D, right? Like if I take something like nickel, it has 4s2 and 3d6, I think, either 3d6 or 3d8. No, 3d6 is iron, so this is 3d8. So it has incomplete 4s, 4p orbitals and incomplete 3d orbitals. So when it undergoes like D shell ke saath hybridization, this is going to show dsp2 or d2sp3 depending on the context. Okay, so that's the difference between d2sp3 and sp3d.
Ma'am, I'm
Yeah.
so sorry, I got disconnected. Could you please explain this again?
No, I was just giving the example, like at what point did you get disconnected, Kaveri?
Like when you were writing the energy levels.
Oh, so sabse pehle. Now I was just explaining the difference between sp3d2 and d2sp3. So if you have the D shell coming from the previous shell, like if you have a 3D and 4s and 4p taking part in hybridization, then you get dsp2 or d2sp3. But if all three belong to the same shell, like 4s, 4p, 4d, or 3s, 3p, 3d, all of them belong to the same shell, then you get sp3d2 and sp3d hybridization.
Okay, got it.
Yeah. And dsp2, d2sp3 is more common with D block elements like iron, nickel, cobalt, manganese, titanium, things like that. P block elements like bromine, sulfur, chlorine, phosphorus, they all you will find only sp3d2 or sp3d. That's like a rule that you can consider it. Okay. One more. Yeah, I was asking about isostructural thing, right? What do you mean by isostructural? Pretty easy to deduce the meaning, you guys.
Bonds with the same structure.
Do bonds have structure or do molecules have structure?
Molecules, yeah.
Molecules. So any two different molecules, or they can be like ion species also, which have the same structure, they're isostructural. Okay. So I'll give you 4 options. You need to figure out which one is a pair of isostructural species. So the first option is SO4 2 minus and BF4 minus. So even if they're ions, you don't have to worry. That just tells you that, oh, it has those many extra number of electrons. You still have to consider, okay, how many atoms is it bonded to, things like that. Like, give it a try. If you guys are stuck, I'll explain it. We'll do the structures and then we'll do it. Okay, so send me the option number of the pair that you think is isostructural. Isostructural in the sense has the same structure. What's up? What's your thinking like? What's going on? Is anyone closer? Like, have you at least, you can figure this out by elimination also, even if you have no idea about what structure could it be. Like, have you eliminated at least like 2 options from the set?
I actually got disconnected. Could you repeat the question?
Oh, do you see the 4 pairs of compounds I've put here?
Yes.
You need to figure out which of these is isostructural. Like, which pair has the same structure? Smera, any idea?
No, ma'am, I'm confused.
No. Rishit? Kaveri, you guys?
Ma'am, I have a question.
Yeah, Adit.
Like when they're saying like they wanted isostructural, so like the hybridization of each are also supposed to be same or what?
Naturally, if the hybridization is same, then their overall geometry also will be the same, right? Whether it's pyramidal or yeah, whatever it may be.
So do we have to find each like हर एक का geometry ऐसा मतलब?
Yeah,
Or
but
like-
there is a hack. Like if you look at the formula of the compounds, you can easily figure out without having to decide the structure for each.
I mean, I do have an
I
intelligent.
eliminated the D one.
D.
I mean, I do have
I
an
think it is
intelligent-
between A and B.
Rishit is confused between A and B. That's very good, actually. You've come.
Yeah, me too.
Arnav is also asking, is it B? Okay. Smera, Kaveri, and Adit, what do you guys think?
I have an intelligent guess though. If I like
Yeah.
though out of 4, probably A because like they're sort of like similar. Like both have 4, so maybe I don't know, or maybe D. But I think it's A. Like out of the 4, maybe.
Adit, nice, good job. That was a rather intelligent guess. And your logic is also like extremely sound. That is absolutely right. So D you can automatically eliminate because we have seen examples. CH4 is methane. BF3 has only like 3 electrons. All of these 3 are bonded. So very different geometries, different structures itself. So it cannot be D for sure. And as Adit said, you can look at it. So carbon dioxide, carbon is attached to 2 oxygens, right? And it has a total of 4 electrons. This also you already know the structure, have a fair idea of it. Do you think carbonate का structure linear हो सकता है?
No, ma'am.
So carbon is connected to 3 different oxygens, right? And it has the ability to bond to 3 different oxygens because of this 2 minus. So original carbon tha, it gained 2 extra electrons. So now it can bond to an extra oxygen. Okay. So that's basically like the gist of it. So it cannot be this also. Ek linear hai, ek pura hai. Yeah, Kaveri is getting the idea. Yes, that is correct, Kaveri. Similarly, nitrogen and ammonium ion. Sorry, ammonia and ammonium ion. I can see why you might get confused between A and B because this is like NH3, NH4 quite close, right? But that's an important difference. NH3 has a lone pair and 3 of these things. That's a good point actually, getting confused between A and B. If they asked about hybridization, then yes, you would be in a fix because NH3, NH4, both of them would undergo sp3 hybridization. Hybridization दोनों में same है, but they're talking about structure, which is why they're different because one is pyramidal and one is like, it has a tetrahedron geometry. Okay. So hybridization wise, they are the same, but structure wise, they are different. And that leaves us with SO4 and BF4. You can see like the most obvious case for it is central atom in both cases is bonded to 4 different atoms. Oxygen in this case, and fluorine in this case. And obviously little bit of difference because oxygen is different from fluorine. यहाँ पे double bond होगा, इसमें सारे single bond है. But the basic structure is same in both. They both will have tetrahedral geometry because the central atom is bonded to 4 different atoms. So this is the correct answer. Okay. All right. So do you have a clearer idea after this question? Like, do you understand how to solve this kind of question?
Yes.
Yes, ma'am.
Okay. Kaveri, Smira, Arnav, Ritu.
Yes, ma'am. Understood.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Awesome. It's 5:20. Few more. Have you guys solved the MCQs from this chapter after the previous class?
Ma'am, on the group, there are MCQs for periodic classification
I don't
chapter,
think there was
not
anything
for
chemical bond.
chemical bonding.
This was not
Yeah.
sent. Oh, array. Then he
Yeah,
should.
so periodic classification on the group you had sent.
Okay. So Fir, I'll send it now, and you guys like go through it. Okay. So I'll send it for VSEPR, VBT, and hybridization. So whatever we have studied. Periodic classification, I'll take it in the next class. And so that's